Okay, we can start.
Thank you very much. Ladies and gentlemen, colleagues, it is our privilege with Professor Kamil Śmierciew, also
Hi,
from
hello.
the same university, to be chairman of this session. We came from Poland, from Białystok, and this session is very particular because it is devoted to ejector applications, various applications indeed, along with application to a refrigeration system and air conditioning. And we are starting the first session of ejector systems with the presentation of the group from Ukraine, from Sumy State University, and Admiral Makarov National University of Shipbuilding from Mykolaiv. And this presentation is prepared by Andrei Lazarenko, Mykola Kalinkevich, and Mykola Radchenko. Professor Mykola Radchenko and Professor Mykola Kalinkevich. And the floor is yours. The presentation will be presented by Andrei Lazarenko.
So, good morning, ladies and gentlemen. The theme of my presentation is design principles for centrifugal compressor diffusers based on the use of velocity distribution. So, first, some introduction. The traditional design of diffusers of centrifugal compressors can be characterized as geometric, in which simple surfaces and lines are used, a plane, a straight line, an arc of a circle, etc., etc. So for vane diffusers, the middle line of the blades is defined by a knuckle of a circle. With such a design, a separation of the flow of pressure surfaces of the vane is typical, while the separation point is located close to the inlet edge. For channel diffusers, when constructing channels with straight walls, the recommendations are used, which are obtained by studying the direct axis gas flow in diffuser channels. The gas flow after the impeller is swirling, and therefore the use of such recommendations for swirling gas flow is fundamentally wrong. Obviously, the creation of new design methods for vane and channel diffusers based on the use of gas dynamic gas parameters, in particular the velocity distribution, while solving the inverse gas dynamics problem, provides the production of diffusers having better gas dynamic characteristics, which improves the performance of the compressors. So for developing methods for designing vane and channel diffusers, the ideas of Stratford were used, according to which a separation criterion would be used to choose the form of the surface of the flowing body in such a way that the spring load of the surface rub in the current flow for an entire hour would be close to zero. Under this condition, the current at the edge of the separation still remains attached to the surface of the body. This allows for not only minimal resistance, but also very low heat flux, since convective heat exchange is associated with surface friction. At the point of flow separation, the maximum pressure gradient is reached. Therefore, for a given boundary layer, the zero friction condition allows to obtain a given allowable pressure increase at the shortest section with the least energy dissipation. So let's talk about the mathematical model. So the swirling flow of the compressible viscous gas is considered. A mathematical model for solving the inverse gas dynamics problem is formed for a steady unbroken flow of gas. So the angular momentum changes for the diffuser inlet to the current values about the axis for the annular element of gas. Here you can see the formula. We shall call it equation 1. So M is the mass flow, RC and alpha in is radius, velocity, and flow angle at the diffuser inlet. And RC and alpha is the current values of the radius, velocity, and flow angle. So moment of forces acting on the vane zone from inlet to the given radius with which B is determined by equation 2, as you can see here, where delta P is the pressure difference on the pressure and suction surfaces of the vane. And after the transformation of the equation 2 mentioned here, the delta M1, we get the equation 3. We'll use it later. So the flow equation using gas dynamic function is given here. We should call it equation 1. So equation 4 and equation 3 in this slide form a system of equation with such unknowns. The unknowns are alpha, lambda PS, and lambda SS. The reduced velocities on the pressure and suction surfaces of the vane and the average velocity are interconnected. The formula for determining the velocity distribution that provides the separation state of the turbulent boundary layer is determined by integrating the momentum equation for the boundary layer and has this form. We should call it equation 5. To determine the separation, the criteria for separation are as follows. And the relative momentum thickness of the boundary layer is determined from the equation 7, where Re is obviously the Reynolds number. So, designing the vane diffuser. The solution of aforementioned equation 3 and equation 4 is performed by the method of successive cross-terminations, and the integral in equation 3 is solved by any numerical method, for instance, the method of central rectangles. Equation 5 used to determine the velocities at the pressure surfaces of the vane, then using equation 3 with the known ratio, the unknown lambda SS is eliminated. The result of a joint solution of equation 3 and equation 4 for number of sections from the inlet to the outlet of the diffuser is the distribution of the rate average flow angles and velocities along the vane. Based on this data, the geometric parameters of the vane and the velocity distributions on its surfaces are determined. The boundary layers are considered in the calculations. The area of the boundary layer is replaced by the displacement thickness, which is determined by this ratio. Equation 7 determines the values of the relative momentum thickness, and then equation 6 determines the value of the form parameters on the second surfaces of the vane. Now about designing the channel diffuser. On the pressure surfaces of the segments, the law of change of velocity is given for the predetermined state of the turbulent boundary layer according to equation 5. The law of change of pressure in the circular direction in the channel and the linear law of change of the average angle of flow along the channels are used. Then, a result of solving the equation system 3 and 4, the change in the average flow velocity and the blockage factor along the radius of the diffuser are determined. The calculation is performed using numerical methods. The calculation of momentum thickness in the boundary layer of the surfaces of the segments is performed by equation 7, and the value of the form parameter is calculated by equation 6. After calculating the boundary layers displacement of the thickness in the channel, the thickness of the diffuser segments is determined by the blockage factor equation that is mentioned below. And the end result of the calculation is to get dependencies such as delta S equals F by R. So let's do some numerical calculation. The simulation of gas flow in the flow part of the centrifugal compressor stage and determination of diffuser efficiency was used in the NCCFX software package for Reynolds numbers more than 10,000 and Mach numbers from 0.2 to 0.6. The calculations were performed for 8 modes of operation of stages, which differed by gas consumption. So in these figures, you can see the differences of loss coefficients and static pressure rise coefficients on flow coefficient. So one is the middle line of the vane is an arc of a circle, and 2 is the given velocity distribution on the surface of the vane. A vane diffuser designed with a predetermined velocity distribution has better performance in nominal mode up to 28%, as well as in all modes with flow rate higher than nominal up to 54%. The static pressure rise coefficient of the vane diffuser designed using the proposed method has a higher value as the nominal mode of 9% and all modes with flow rate more than 21%. The prospect of the proposed vane diffuser profiling method with a given velocity distribution on the vane is obvious. In the ANSYS CFX software, a channel diffuser was calculated using the proposed method. The characteristics of the traditional channel diffuser and channel diffuser which profile was obtained using the above method are compared. The diffusers have the same geometric dimensions but different segment profiles. So this figure 2 shows the segment profiles and diffuser characteristics obtained in SCCFX. So as you can see, the design channel diffuser is more efficient than traditional one, particularly in all modes. And in the calculated mode for this diffuser, the value of the static pressure coefficient is higher by 32%, and total pressure loss coefficient is lower by 30%. So also experimental research was done. So experimental investigations of the diffuser model, which was designed using the presented method, were made at the aerodynamic stand. Figure 3 shows the scheme of the used experimental model. The design pressure distributions along the midline and along the surfaces of the channel diffuser segments were confirmed experimentally. And here, figure 4 shows the distribution of relative static pressures along the surfaces of the segments. The discrepancy between theoretical and experimental values of the pressures at the corresponding points did not exceed 2%. Here, figure 5 shows experimental and theoretical loss coefficients obtained for different sections of the channel diffuser. Discrepancy didn't exceed 15% for all modes of operation. With the reduction of the mass flow of gas, the losses increase more intensively than in case of an increase in flow rate. So conclusions of my presentation, of our presentation, sorry. A new method of designing vane diffusers with a predetermined velocity distribution on the vane surfaces provides an improvement in the gas dynamic characteristics of diffusers compared to traditional geometry diffusers, which has reduced losses from 28 to 50% and increased values of static pressure rise coefficients from 9 to 21% in a wide range of modes. The proposed method for profiling centrifugal compressors channel diffusers allows to reduce the calculated mode losses by 30% and to increase the value of the static pressure rise coefficient by 32% compared to traditional geometry channel diffusers. Thank you for your attention.
Thank you very much. Thank you very much indeed for your great presentation, just because you are just on time. So we have 5 minutes for questions. Unfortunately, people do not decided to ask the question as far as I see. Hello?
Yes, I'm seeing also that there is no question in Slido, so we have to fulfill the 5 minutes.
Yeah, maybe we should just to say a few words, just because indeed issues concerning finding of separation points in the design procedure in the diffuser or vane compressors are very important. Maybe I have one question, just because I didn't catch exactly the idea. In the analytical approach for the design, you are assuming linear distribution of pressure, or what is about the pressure distribution in the analytical model you have applied in design procedure?
I'm terribly sorry, I didn't quite get the question. Could you please email us, because the quality of the connection is really bad.
Okay, so the experiment was done with air as working fluids in the experiments you have presented?
Yes. So I quite didn't hear the question. I'm sorry. The connection is really bad.
You have presented us the experimental, the results of experimental investigations.
Yes.
And indeed, it is very interesting because you have presented the analytical approach for the design.
Yeah, the mathematical model, yes.
And then CFD comparison with the analytical simplified approach and experimental results. So it looks pretty good. So that my question, just because we are coming to discuss also refrigeration issues, you probably have applied air as working fluid in the experiments.
Air?
Air. Or
just 1 second. I will ask a question. Okay, 1 second. For the simulation in SSCFD, we only use the model of the compressible perfect and ideal gas, only this model.
Perfect ideal gas, but air, I guess.
Yes.
Yeah. But I guess this model is applicable also for the other types of fluid, I guess.
Yeah, we have plans to do some more tests on different types of fluids. Yes.
And when you done the CFD, it was a 2D or a 3D model in your CFD?
It was a 2D model.
2D. Okay, thank you very much.
So maybe it is time for our second presentation. Can we start it just now? Maybe I will prepare this. It is seen?
Yes, we can see it.
Okay. And this is, maybe you can just say, Kamil, a few words in the introduction.
Okay, so the presentation will be provided by Professor Butrymowicz. He's a leader of our group from the Białystok University. And this presentation is related with air conditioning system in Moto Yacht. The system is operating with the ejector and is driven by waste heat taken from the combustion engine. So you may start right now because
yeah. So I have only 12 minutes. So,
yes.
ladies and gentlemen, colleagues, I will be talking very shortly, of course, about the maybe engineering issues, not very scientific, just because we are running with the project with the Polish shipyard, so that two people for this presentation are from Marine Projects Ltd. It is the shipyard located in Poland, Gdańsk, which is manufacturer of medium and small size of various types of ships, motor yachts, special cranes, special ships, and with over 30 years of activity in this market. And this is the reason this company will be interested, maybe as a first, to implement not only the ejection refrigeration system in order to utilize waste heat generated by diesel engines. So that's, I will be talking shortly about the ejector refrigeration systems in the version which have been applied. And then just a few words about application of the second wheel, and then our results of the analysis of air conditioning cycles, which will be combination of ejection refrigeration system and desiccant wheel, and conclusions. So maybe it is not very useful to just discuss the concept of the ejection refrigeration system, because I do believe that it is obvious for most of the audience. So the difference between the compression system, which consists in the evaporator, expansion valve, condenser, is the application of the supersonic ejector, which is driven by vapor that is generated in the vapor generator, and liquid pump is just for pumping of liquid to the vapor generator. And well, the point is, if you have the diesel engine, also in marine applications, you have a lot of the waste heat, and the point is to use this heat to drive the refrigeration system and other elements of the air conditioning units. So that's the most useful part. It will be exhaust gas and also jacket water cooling. And this is the main part we are using. Of course, the other sources are possible. And but these two are the most convenient to be applied to drive the air conditioning units. And therefore, if you can see the relationship between the flue gases flow rate, which is a result of the engine pressure and load, because it is a very unique situation that the ship is going with full load. In most of the cases, you have 70 to 80% of the load during real operation of the diesel engine machinery. And you see the relationship between available temperature of the exhaust gases and thermal power. And you see what will be the range of temperatures we have. So these data taken from the ship owner data for the diesel engine we have in selected ships, so that it is general layout of our system. So it is composed, well, we are doing the entire exhaust system. So this system is composed of we have diesel engine, and first we should build a waste heat recovery system in order to recover the waste heat from the flue gases. In our case, we have maybe it is a unique situation, but we have applied steam, water steam recovery system. It is really operating in marine applications, because due to safety reasons, you may not apply just flue gases to drive the system directly. And this is our ejection refrigeration system. It is our design of waste heat recovery system. And the third subsystem, I will not be talking about in details because it is out of scope of this presentation. It is scrubbing system. It is our concept of utilization of two-phase mixing shockwave for scrubbing to also eliminate impurities from the flue gases in clean gases. So these are our scrubbing devices. So at the end, you see that we utilizing waste heat and also do cleaning of the exhaust gases in one system. And this is the layout of the schematic of the prototype steam heat recovery system. And so it is maybe the most useful way to do that, and in the case of the marine applications. And you can see how it looks, the spatial schematic of this system. It is this is the flue gases heat exchanger, and this is the condenser. So here we have generation of steam. So we are taking heat from the flue gases. So we have assumed that here we can just produce in the condenser the condensation process temperature, which is enough to have evaporation, which have the maximum temperature of the refrigerant inside the ejection refrigeration system, 120 centigrade. In our case, you can see just it is look out of the. In fact, it is a combination of hybrid ejection, compression, refrigeration system. So I don't have possibilities to discuss this in details during the short presentation, but in fact, it is a kind of hybrid ejection and compression refrigeration system. So we have two systems in one unit. And this is this heat exchanger, which is applied to heat recovery. And as a first approach, we have decided to apply refrigerant 1234ZEE. However, it is A2L classification. Just now we have moved to the another refrigerant, which is totally safe, belonging to A1 group, but you can see the ejection refrigeration cycle here. So it is the motive temperature, the maximum motive temperature. So we have supercritical cycle in this case. And as a first approach, we have assumed that will be 5 centigrades of evaporation temperature. So that we have also discussed the possibility, the design of the ejector in the ejection refrigeration system to have evaporation temperature 0 or 5 centigrades in order to meet the requirements to production of chilled water at the level of 5 Celsius centigrades or 10 Celsius centigrades. And well, concerning the marine air conditioning units, we have a huge problem. What is the problem? So I have listed, maybe I will not read them, the required operation conditions for marine air conditioning. You see, you should assume that temperature outside is 35 centigrades and humidity 70%. What does it mean? You should have such situation that you have huge latent heat that should be removed. And due to such conditions, you have very, very high thermal load of the evaporator or refrigeration system because of such relative humidity. So, it is really a huge problem what to do just because you need a lot of refrigeration capacity to do that. And you also should assume that seawater, you have 32 centigrades for your system. That is the reason we have decided to change the conventional approach in the air conditioning unit to apply a desiccant wheel, which is very similar to that wheel which is used as a regenerative heat exchanger in air conditioning units. And we have here regenerative section and desiccant section. And if you have the exhaust air, it is heated up and it causes dry out of this section. And if this section is dry out, you can just dry out this process air in a wheel. So this is in fact the picture which shows us the ejection refrigeration system, which takes the waste heat in this heat exchanger. So this is in fact water as a refrigerant here and refrigerant, HFO refrigerant here. and this is a conditioning unit. And if you have exhaust air, then this air is going to the heater. We are using this waste heat to heat up this air in order to feed it up to regeneration section. Sorry. And concerning the fresh air, it is mixed with exhaust air, and then it's going to the second section of the desiccant wheel, and is dried out and heated up, so that first this is cooled down in the intercooler. Because of high temperature, you can see you can use seawater to preliminary cool down the chilled water, and then air, sorry, to cool down the air, and then is going to cooler, and you need refrigeration capacity only here. And so this approach creates possibilities to apply as large as possible application of waste heat in the air conditioning units, and reduce a refrigeration capacity that is needed by air conditioning system. And also, you see, it is possible to use also very high evaporation temperatures. So first, you have eliminated as much as half of refrigeration capacity. And the second point, you can increase evaporation temperature so that your refrigeration system independently will be compression, ejection, whatever it could be, will be much more effective. And here are listed for the selected motor yachts heat gains and sensible heat gains and latent heat gains, so that we have 22 kilowatts of refrigeration capacity in this case, and the ratio delta H to delta X due to also latent heat due humidity calculated, and required a flow rate and fresh rate also for this yacht. Well, maybe we don't have enough time to discuss in details issues concerning the air conditioning cycle. This is the conventional. So the latent heat is produced, is covered by the refrigeration capacity produced by the compression refrigeration system or ejection refrigeration system. It is the conventional approach. In this case, we need as much as 50 kilowatt. So you have heat gains 22 kilowatt, but your refrigeration capacity required is almost 50 kilowatt. If you apply desiccant wheel, so this is operation of desiccant wheel, heating and drying of air, and it is the heat which is heated up and dry out, and drying, here is drying of the wheel, of course, not air, and here's drying of air and cooling in the intercooler, and then in the cooler of the refrigeration system. And here you need a thermal load of the evaporator 24 kilowatt only. So it is half of that. And moreover, the system is very efficient because you require evaporation temperature not 0 centigrades but 12. You need, so that the motive heat required for the slightly modified ejector refrigeration system is only 50 kilowatt. It is much less than you have from the diesel engines. So in our opinion, it is the best approach to do that in the case of the marine applications with use of the waste heat from the diesel engine. So and
Darius,
this is
you have 1 minute.
Yeah, of our air conditioning units which have been applied. So we are during the tests of this system under marine conditions. So I have presented during in this presentation the practical approach, how to use effectively waste heat from the diesel engine in marine applications to not only drive the ejection refrigeration system, but also to utilize to prepare the comfort conditions by means of the desiccant wheel. Okay, so thank you very much for your kind attention.
Thank you very much, Darius. And I see that there is no question for this presentation, so maybe we can go.
I'm sorry, I have one question, if it's possible.
Okay, so one question.
Yes. Can you tell me what coefficient of performance you can reach if the temperature of boiling refrigerant is the same, about 12 degrees centigrade? The temperature of hot water as a source is about 90 degrees centigrade, and the temperature of condensation will be, I think, about 45.
45.
Yes, 45.
30 or 40? 30.
40.
No, if you have 45 centigrades, it is problematic just because probably you are operating under off-design operation conditions, and you should be carefully study whether such operation is possible. It is possible, but probably your coefficient of performance is not very good. So condensation temperature is very important. If you can decrease condensation temperature, and if you have 12 centigrades evaporation temperature and 90 centigrades, you can have a coefficient of performance as much as 0.5, even 0.45, something like that. It is possible. But the problem is with condensation temperature. If you have condensation temperature 35, 33, I guess it will be possible. If you have 44, it is really very problematic. Probably you can do that, but with COP, which will be significantly lower. Kamil, maybe you can say something, but I guess that will be not.
We don't have time for this kind of discussion right now, so we really should go to the next presentation.
Yeah, okay. But thank you very much for your question. Okay.
Yes.
So I just.
So the next presentation will be provided by Halina Kobalova. It is a pre-recorded video, so we can start it.
But the organizers tells us that.
Hello everyone, I'm Galina Kobalova. I work at Admiral Makarov National University of Shipbuilding at the Department of Thermal Engineering, and now I want to present you our team research from Dmitro Konovalov, Mykola Radchenko, Roman Radchenko, and Vyacheslav Svidel. This research dedicated to define improving the efficiency of gas turbines by using an IIR thermopressor for intercooling cyclic air. So let's start. Complex cycles with cyclic air intercooling are used to increase the energy efficiency of gas turbines. One of the promising ways to increase the efficiency of gas turbines is to use air intercooling at the compression process in the compressor. As you can see on the left side, the apparatus called IIR thermopressor is installed between the compressor stages. In this scheme, the IIR thermopressor is used for contact cooling of cyclic air. The IIR thermopressor, scheme of which is presented on the right side, is a two-phase jet apparatus in which the air pressure and air cooling are increased by removing heat from the airflow. With proper organization of the evaporative contact cooling process, the effect of thermogas dynamic compression is taking place. One of the perspective ways to increase the power of gas turbine engines is to increase the flow rate of the working fluid with a decrease in consumption for compression in the compressor stage. The way to implement this principle is to use the contact air cooling with the IIR thermopressor. This research is dedicated to investigate the IIR thermopressor operation by using CFD simulation and to analyze the efficiency of IIR thermopressor used for contact intercooling of cyclic air in the gas turbine circuit. The IIR thermopressor model and boundary conditions are shown on the left side. The model has following geometrical characteristics. The thermopressor length is 1324 millimeters. The evaporation chamber diameter is 68 millimeters, while the flow rate is 1.56 kilogram per second. The parameters of the airflow at the thermopressor inlet, such as velocity, pressure, temperature, air mass flow, Mach number, you can see at the table. They correspond to the parameters of the cyclic air between the compressors of the gas turbine. Water droplets were taking spherical shape and were injected in the same direction as flow. Simulation of water evaporation process was carried out by using computative demodeling techniques. LN Lagrangian model was used to compute the two-phase flow. The calculation is carried out in the following order. First of all, the airflow was calculated without taking into account the influence of the injected water droplets. After that, we calculated the discrete phase in the Lagrangian approach based on the calculated airflow field. Then, the main parameters of the two-phase flow at the IIR thermopressor outlet were defined. And finally, we simulated the thermopressor operation and determined of gas turbine main characteristics with intercooling by using IIR thermopressor. To define characteristics of the IIR thermopressor workflow, the developed software was used. It was based on calculating thermodynamic compression method. A feature of this effect is an increase in pressure as a result of instantaneous evaporation of injected liquid in the airflow, which accelerated to the speed of sound. Pressure losses due to the aerodynamic resistance of the two-phase flow in the IIR thermopressor flow path were included. As a consequence of the influence reversal load during contact evaporative cooling of the airflow, it was found that the main effect is determined only by thermal effect, which is associated with the heat consumption for the evaporation of the injected liquid. Therefore, regardless of the quotition value, the pressure and density parameters grow during the water evaporation in asepsonic flow. Obtained results. At the first stage, a simulation of the IIR thermopressor was carried out. It was found that the decrease in the airflow pressure due to frictional losses is 15 kilopascal or 5%. The air velocity at the inlet of the evaporation chamber was 280 meters per second. The diffuser divergent angle ensured the absence of flow separation, which reduced local pressure losses in the diffuser. At the second stage, the IIR thermopressor was simulated with water injection into the flow path at the evaporation chamber inlet. The results demonstrate that with incomplete evaporation, with obtaining smaller droplets at the outlet from the diffuser part, the increase in total pressure is 4.5 kilopascal or 3% relative to the inlet pressure. The magnitude of the cyclic air cooling in the compressor with incomplete evaporation is 280 degrees. The mass concentration of water that didn't evaporate at the IIR thermopressor outlet at the diffuser outlet was 0.11 kilogram per cubic meters. This water should evaporate already in the flow part of the gas turbine compressor. Distribution of dispersion of water which is spread in the flow path of the IIR thermopressor is shown on this slide. You can see the dispersion of water droplets at the evaporation chamber. inlet was the evaporation chamber inlet was in accordance with the characteristic of the nozzle. It's 15 microns. As a result of contact evaporation, the diameter of the droplet decreased, and at the diffuser outlet water didn't evaporate. The dispersion average was in this case was almost 3 microns. In this case, the concentration of water droplets at the outlet is observed closer to the axis of the diffuser and has a diameter almost 50 millimeters. Comparison of the change in pressure, these two lines, along the lengths of the IIR thermopressor with and without water injection shows that the pressure in the evaporation chamber decreased from 240 kilopascal to 235 kilopascal due to losses. That is, the pressure loss is 5 kilopascal or almost 2%. However, the presence of thermodynamic compression increases the pressure and compensates for these losses. In this case, the total pressure in the evaporation chamber in this place increases by 15 kilopascal or 5%. The IIR thermopressor operation as part of the gas turbine was simulated. The apparatus was used for contact cooling of cyclic air between low and high pressure compressor stages. Depending on the total compressor ratio, the cyclic air temperature between compressor stages was decreased by 130 degrees. Such temperature degrees under thermodynamic compression conditions allows increasing the pressure from 4 to almost 11%. A decrease in the compressor operation and a simultaneous increase in the amount of the working fluid in the cycle makes it possible to increase the gas turbine efficiency by 2% in comparison with intercooling of air by using a surface air cooler. In this case, the specific fuel consumption will decrease by 5 gram per kilowatt-hour. At the same time, the gas turbine specific power is increased by 5%. So, conclusions. The main of which is that the thermopressor provides effective fine atomization of water. The droplet's diameter at the outlet from the apparatus does not exceed 3 microns, and therefore a more effective isotherm of the compression process in the high-pressure compressor could. A decrease in the compressor operation and an increase in the amount of the working fluid in the cycle makes it possible to increase the gas turbine efficiency by 2% in comparison with the cooling of air by using a surface air cooler. So, my presentation has been finished. Thank you for your attention.
Thank you very much for your kind presentation. And I see that there is no question in the from the audience. So maybe some from the audience here have some question. If yes, we have maybe time for one question, if any.
Thank you. No question.
Thank you for your attention.
So it's 11:15. Maybe we should start the next presentation. The next presentation will be given by Professor Mykola Radchenko. It is also
Anyway, I think that we should say just it was really great presentation, and the paper was combined, great efforts and the combination of advanced modeling and experiment and just some important ideas. So I guess that should be some important question, but we don't have enough time to discuss the paper. So there is no question does not mean that the paper was not interesting. So indeed, I will have a lot of questions concerning modeling, and a combination of two-phase flow and ejectors are also many open issues. So congratulations concerning your paper. So, but we need to go to the next presentation, unfortunately. Thank you.
So we would like to ask the moderator to start the video for the next presentation.
Good day, dear colleagues and friends. My name is Mykola Radchenko. I am a head of Condition and Refrigeration Department of Admiral Makarov National University of Shipbuilding, Nikolaev, Ukraine. Let me introduce some results of our investigation together with our colleagues in the Gdansk University of Technology, Poland, in the field of injector refrigerant circulation for enhancing heat efficiency of air coolers with uneven heat load distribution. The operation of conventional as well as mini-channels evaporators air coolers is characterized by uneven outside heat loads as well as by refrigerant maldistribution in manifolds and between channels. The final stage of full refrigerant evaporation in channels of evaporators air coolers involved dry out regime is characterized by sharp drop in evaporation and overall heat transfer intensity and heat flux as a result. The existing methods of refrigerant redistribution in inlet manifolds by using the special insertings lead to increase of pressure drop of air coolers and is not efficient in actual operation in changeable heat loads. The aim of research is to develop a general concept of incomplete refrigerant phase change through injector refrigerant recirculation for new application in mini-channel plate evaporators affected by uneven refrigerant distribution in manifolds and uneven air-side heat loads, as well as for outdoor air processing units to match varying heat loads according to actual climatic conditions, and for indoor fan coils to match varying indoor heat loads in variable refrigerant flow systems. The main equation used in methodology are presented here. Here you see the overall heat transfer coefficient and logarithmic temperature difference and heat flux as a result in dependence on refrigerant mass velocity. The opposite influence of refrigerant mass velocity on overall heat transfer coefficient and logarithmic temperature difference causes the existence of maximum value of heat flux, and corresponding mass velocity could be considered as optimal value. Here you see in the picture A typical structures of inside tube refrigerant evaporation and variation of coefficient of heat transfer to refrigerant in bubble zone, convecting evaporation, and mist flow in in post dry out regime are presented in figure A. And heat transfer to boiling refrigerant, air side, and overall heat transfer coefficient, and heat flux as a result, independent of vapor mass fraction, are presented in figure B, E, C. In order to exclude dry out wall regime, followed by sharp drop in boiling refrigerant and overall heat transfer coefficient, and heat flux as a result, it's necessary to operate at mass vapor quantity less than critical value, less than this value. Through tube overfilling by liquid refrigerant. Here you see the variation of heat flux against refrigerant mass velocity for number of circulation equal 1. It's for conventional air cooler with complete evaporation. You see this curve. And for number higher than 1, it's for incomplete evaporation with liquid refrigerant recirculation. As you see, recirculation of a liquid refrigerant in a cooler by injector provide an increase in heat flux by about 25–30% as compared with traditional full evaporation. Overfilling the air coils of air cooler by recirculation of liquid refrigerant enables a larger, more than 50% deviation of refrigerant mass velocity from its optimal value, as compared with traditional deviation with the full evaporation of refrigerant inside channel. Thus, a larger heat load changes are permitted that gives good perspectives of injector liquid refrigerant recirculation for air cooler with variable heat loads and refrigerant melt distribution. Here you see air velocity profile of air at the inlet of air cooler, and heat load distribution for tubes of different number. This heat load distribution for air cooler with full evaporation, and this heat load distribution for overfilled channels. As you see, increment in heat flow rate is about 40% due to incomplete refrigerant evaporation. Here you see the typical scheme of the refrigeration machine with full evaporation, and proposed refrigeration machine with injector circulation of liquid in evaporator. The liquid refrigerant circulation by injector with the number of refrigerant circulation of about 2 with mass vapor fraction at the inlet of about 0.5 satisfies these requirements. Here you see the example of application of ejector liquid recirculation for variable refrigerant flow system. This is the typical traditional ductless variable refrigerant flow system with outdoor air processing unit and indoor unit. And here you see the developed variable refrigerant flow system with liquid refrigerant recirculation by injector in outdoor and indoor air processing units. Innovation author solution consists in that liquid refrigerant recirculation by injector with a number of refrigerant circulation of about 2 enables to cover 70% of increased heat loads. Here you see the example of application of injector circulation in mini-channel evaporators. A developed vapor compression chiller sockets with injector liquid refrigeration in mini-channels is presented here. The principle of overfilling all the channels by liquid refrigerant injector recirculation provides excluding the final dry out stage of refrigerant evaporation with low intensity of heat transfer, and it's very useful for microchannel evaporators characterized by uneven refrigerant distribution in inlet manifolds. It's a preferable alternative to refrigerant distribution in inlet manifolds by using the special insertants that lead to increase of pressure drop of air coolers and is not efficient for changeable heat loads. So instead of solving the problem of refrigerant distribution between microchannel planes, it should be solved by overfilling the microchannels. The refrigerant circulation provides suppressing the bubble generation initiated by heat flux and leading to instabilities of two-phase flow that can lead to instantaneous dry out of the valve with sharp drop in heat transfer intensity and even to reversing the flow towards the inlet with blocking the refrigerant feed to channels. Conclusions. A developed concept of enhancing heat efficiency of air coolers is intended to solve the problem of uneven outside heat loads as well as of refrigerant maldistribution in manifolds and between channels by overfilling all the channels through injector liquid refrigerant recirculation that provides excluding the final dry out stage of refrigerant evaporation with sharp drop in evaporation heat transfer and intensity of overall heat transfer and heat flux. The application of liquid refrigerant recirculation by jet pumps allows to match actual changeable heat loads, not by varying refrigerant feed to throttling air coolers as in variable refrigerant flow system, but supplying excessive refrigerant flow to air coolers with the overfilling at any peak load to provide efficient operation without drying out the inner walls of air coolers. Thus, the liquid refrigerant circulation system operates as self-controlled due to presence of linear receiver and the liquid separator receiver, both fluctuating as cooling capacity accumulators. The principle of overfilling all the channels of air coolers excludes any influence of inside channels heat transfer and is very useful for microchannel evaporators with uneven refrigerant distribution in manifolds as well as for conventional heat exchanger with uneven air velocity distribution. Thank you for your attention. Thank you.
So we don't see any questions for this presentation. Kamil, do you
I don't see it either.
So Professor Radchenko, it is. I think that there should be. Okay. I have some. Really, this concept you proposed is interesting, just because it is just presentation of the concept of usage of two-phase ejector, not as a booster compressor to improve efficiency, but to improve to enhance heat transfer. But my question is, have you analyzed also this concept for the other refrigerants than R141B?
I should say that all the refrigerant has such peculiarity that at the end of full evaporation, heat transfer coefficient and overall heat transfer coefficient and heat flux at result fall. I think the vapor fraction is within 0.8 0.9, so it's quite typical for, I think, for majority of existing refrigerants.
What will be also interesting for CO2, because people are using this kind of ejectors to improve efficiency of the system and do not pay attention that you can enhance heat transfer also by using of such ejector, right? So it is the second positive aspect which could be obtained.
I should say that the most important point I pressed here in this report, that recirculation of liquid refrigerant in evaporator enable to wide heat load deviation, from nominal value. So it's very useful for real operation of any refrigeration system. And I think that this could be done for different types of evaporators and even for mini channels without improving, by insertance and so on. Thank you very much.
Thank you very much. Thank you.
Thank you very much.
Just we have the last presentation for this session, and this will be provided by Professor Sherry Sarapov from Summer State University. In fact, I am one of the co-authors of this presentation. Okay, so
thank you so much. Good day, dear colleagues. I very proud to be present in this conference, and I would like to present you a report on the topic efficiency of a vacuum cooling system with liquid vapor ejector for biodiesel production. So I would like to present our international team of authors. There are 3 authors from Sumy State University, my colleagues Maxim Prokopov and Viktor Kozin, and I'm very happy that I have so authors Darius Butrimovich from Bialystok University of Technology. We should know that at the present time, a lot of researches have been conducted all over the world that aim of ensuring a fuel economy and replacement of traditional energy resources. Those may be exhausted in the near future. Biodiesel is a type of fuel that may be replaced oil diesel fuel. European countries are absolutely leaders in the production of and using of biodiesel. The feature of biodiesel production is the purification of the initial products from odorants that are carried out under pressure below atmospheric. A modern industry uses the vacuum system that you can see on the slide that shown as a basic vacuum cooling system and a basis of steam jet ejectors. There you can see 3 stage ejectors that are named as 1 booster first stage, second booster stage, and 4 is a third stage steam ejector, and with intermediate capacitors. There are biggest of this scheme is a low efficiency in level from 2 to 10%. So in this situation, the using of liquid vapor ejector working on this principle of the steam thermal jet thermal compression becomes very relevant. On this slide, you can see the vacuum unit based on the liquid vapor ejectors. There is liquid vapor ejectors, separator, heat exchanger, and circulation pump. There is also, you can see a cycle in pH diagram that is describes the liquid vapor ejectors based on the steam thermal compression. This principle differs from the traditional that the generation of working steam occurs inside the cycle in the motive flow nozzle. So there are no an equipment that may generation working steam. The generation of working steam is in the liquid vapor ejector. So we decided to change three-stage jet steam ejectors for one stage vacuum unit based on liquid vapor ejectors, as you can see on this slide. As a second stage is a liquid marine vacuum pump that is shown there on figure 6. So the main aim of our influence of the is influence of geometric parameters of the flow path on the ejector on the efficiency of biodiesel production system. There are numerical investigations of 4 ejectors that is differ the form of the mixing chamber and diffuser. First was the liquid vapor ejectors with conical mixing chamber and diffuser. Second was ejector with conical mixing chamber without diffuser. Third was the ejector with a cylindrical mixing chamber and diffuser. And the fourth was ejector with a cylindrical mixing chamber without diffuser. So there was an experimental investigations. Experimentally was investigated the liquid vapor ejector of different design according to slide 6 on previous slide. The parameters of the working fluid are the inlet of the motive nozzle was flows pressure in ratio 0.3, 0.6 megapascal. Temperature in the inlet was 120, 150 degrees of Celsius. Parameters of the working fluid in the secondary flow and the inlet of the suction chamber pressure is in ratio 0.03, 0.055 megapascal. Temperature is a ratio of 40 from 40 to 90 degrees of Celsius. The parameters of the mixing flow in outlet of the liquid vapor ejector were the follows. Pressure in the outlet is 0.04 and 0.1 megapascal. Temperature is 70 and 100 degrees of Celsius. Distribution of pressure is one of the most parameters that we are investigated, and you can see on this slide the distribution of pressure in 4 of ejectors that are the results of a numerical investigation. This slide presents a result of experimental and numerical investigations of liquid vapor ejector with different design that describe changes of operation parameters in the actual direction, such as pressure. Lines is numerical results, and the points is experimental design. Colors are according to slide 6 with ejector with conical mixing chamber and diffuser, conical mixing chamber without diffuser, cylindrical mixing chamber, and with diffuser, and cylindrical mixing chamber without diffuser. From this slide, you can see that in the liquid vapor ejector with the diffuser, we have more uniform pressure distribution in the mixing chamber of both cylindrical and conical mixing chamber. The rate of the mixing chamber flows at the outlet of liquid vapor ejector with the diffuser is less than the similar liquid vapor ejector without the diffuser, which more favorably affects and completeness of the mixing process. On this slide, you can see distribution of velocity in the liquid vapor ejector. So it's results of numerical investigation in NCCFX. On this slide, you can see the distribution of velocity. The legend of this graphic is the same as in a previously slide. So numerical results as the lines and experimental results as a point. You can see that liquid vapor ejector without diffuser with conical or cylindrical mixing chamber, in the outlet we have more in the outlet we have the mix and flow with more speed, as you can see, and in conical and cylindrical mixing chamber. Vapor mass fraction in the flow part are described in this channel. From this slide, you can see that in the liquid vapor ejector with diffuser and conical mixing chamber, it also will be more described in this graphic. With diffuser and conical mixing chamber, the mass vapor content is the optimal level. X out is 0.12, and considerably the degree of steam production is close to C out steam production, 1.17. In the liquid vapor ejector with diffuser and cylindrical mixing chamber, the degree of steam production in the mixed flow is higher. C out is 1.42, and the liquid vapor ejector without a diffuser, the degree of steam production continue to increase and is a level contained to a level C out 2.27. Also, we give an exergetic efficiency of liquid vapor ejector and separator. There you can see flows inlet, primary flow, secondary flow, and outlet flow. There is a exergetic schema of exergetic flows in liquid vapor ejector and separator. Also, we have exergetic efficiency of vacuum unit based on liquid vapor ejector. There you can see vacuum unit and the scheme of exergetic efficiency. Exergetic analysis was used by George Ciceronis method. The results of exergy analysis is shown on this slide. The numerical results are shown by lines and the experimental results are shown by points. There you can see the exergetic efficiency of liquid vapor ejector, exergetic efficiency of vacuum unit based on liquid vapor ejector, and the coefficient of an injection of liquid vapor ejector. So as a conclusions, we may say that after analysis of the effect of liquid vapor ejector design parameters on the efficiency of vacuum cooling system of biodiesel production unit, the following conclusions can be drawn. The use of liquid vapor ejector made it possible to simplify the design of the unit by switching from three-stage steam jet ejector to a single-stage vacuum unit based on liquid vapor ejector. The use of liquid vapor ejector allowed to reduce the initial parameters of the working flow steam by switching to more moderate parameters of the working water in liquid vapor ejector primary flow from 0.9 megapascals and 225 degrees of Celsius to 0.4 megapascals and 135 degrees of Celsius. The use of liquid ejector allows to minimize the consumption of working steam due to the design features of the vacuum unit based on liquid vapor ejector, where the working steam is consumed not as a primary flow of the steam jet ejector by only a small amount of heating the working water of the primary flow in the heat exchanger, reducing steam consumption from 1,535 kilograms per hour to about 216 kilograms per hour, which is less than 7 times. The use of liquid vapor ejector without a conical or cylindrical mixing chamber without a diffuser makes it possible to obtain a flow or a uneven structure at the outlet of the ejector due to a high flow rose in the flow path and the incompleteness of the mixing process in the chamber. This fact requires the placement behind the mixing chamber of an additional cylindrical section to align the final flow parameters at the outlet of the ejector. Therefore, due to the above, liquid vapor with a conical mixing chamber with the following cylindrical part and the diffuser, slide 6A, is the optimal for this unit. Thank you for your attention. I'm finished.
Thank you very much for your presentation. It was very interesting. So it was the last presentation, so maybe we have time for some questions, if any.
Yeah, I have question.
Yes, okay.
Okay.
Yeah, okay, please.
Please tell me what type of turbulence model did you use in your research?
By modeling in NCSTFX, we used the K epsilon model of turbulation that was programmed on this complex.
Okay, thank you.
Thank you so much.
Okay, are there any other questions?
No questions. Thank you.
No questions.
Some people would like to move to the another session just because in the another sessions maybe there are some
Yes, of course.
Okay, so this is the end of the session, so just now we can encourage people. Thank you very much indeed for your presentations. In fact, these are presentations from Ukraine, so the papers are pretty good and presenting new ideas, new concepts, and great developments in modeling experimentations in two-phase, one-phase ejectors, as well as centrifugal compressors. So I do believe that this great development of the research. So independently of the situation, so I encourage also you to try to publish the papers in the journals, just because most of the papers presented really very developed research, not only calculations or ideas, but also supplemented with experimental validation. So they, I guess, may be published in the journals. And we should just encourage you to participate in the second session. It will be 3 p.m. But before, there will be invited paper session, which will be, I guess, 1:30. Kamil?
Yes, yes.
1:30. 1:30. So just now, thank you very much for your participation. To all of the attendants, maybe not visible, but we also would like to thank you for your attention and participation in the session. Thank you very much.
Thank you so
Okay.
much.
Thank you
Thank
very
you.
much
Okay, thank you. Bye.
for kind promoting